In April 2026, Google released Gemma 4. It provided developers with a highly capable, open-weight AI model designed to be downloaded and run locally, entirely offline. Within days of the launch, the model was quietly pulled from Google's consumer-facing interface, AI Studio. The retraction was triggered when the model generated a detailed, defamatory narrative concerning Senator Marsha Blackburn. The output included fabricated criminal allegations, referenced non-existent individuals, and cited fake news URLs to substantiate claims. Political pressure mounted immediately. Senator Blackburn sent a formal letter to Google CEO Sundar Pichai denouncing the output as an act of defamation and escalated the issue during a Senate hearing. Google shut off access to Gemma 4 via their hosted platform. But because the foundational weights were already distributed as open-source files, any developer could still download and run the exact model on their own machine. Centralized cloud APIs intercept queries behind a wall, allowing companies to filter outputs and enforce strict safety policies. Local deployment grants direct access to the weights, bypassing those external filters entirely. Gemma 4 was architected explicitly for this local environment. The model relies on three specific engineering pillars: a mixture of experts routing system, native multimodality, and an Apache 2.0 license. Optimizing an AI model to run locally on consumer edge hardware forces a permanent shift in how safety is managed. Once a highly capable model executes locally on consumer hardware, the original creators lose the physical ability to retroactively patch its behavior. Gemma 4 represents the exact moment where the base capabilities of local models outpaced the control mechanisms of centralized cloud containment. Local developers face strict hardware realities. Consumer-grade GPUs have severe VRAM limits compared to the massive accelerator clusters used in data centers. This diagram shows a standard, dense neural network. During inference, a dense model activates every single parameter for every process token, which maximizes VRAM capacity and creates extreme latency on consumer hardware. To solve this compute bottleneck, Google engineered the 26 billion parameter mixture of experts, or MOE variant. While the MOE model holds 26 billion parameters, it introduces a routing layer. This mechanism sends an incoming token down specific pathways, selectively activating only the relevant expert nodes. Out of 26 billion parameters, only 3.8 billion are active during any single step. The practical result is a massive increase in tokens per second, allowing the model to run fast and efficiently on a single consumer graphics card. This sustained speed is what permits complex agentic workflows. Tasks requiring multi-step planning and deep logic can now execute locally without timing out. The mixture of experts architecture decouples theoretical intelligence from immediate hardware limits, putting enterprise-grade AI offline. Alongside the MOE model, Google released a 31 billion parameter dense model, optimized entirely for raw statistical quality over low latency execution. Unquantized, the 31B dense weights require a single 80 GB H100 GPU to run efficiently. We can measure the precise logical capabilities of these models using the Arena AI Text Leaderboard, the industry standard for comparative blind-tested evaluation. This ranking chart shows the 31B dense model securely holding the number 3 position globally among open models. The highly efficient 26B MOE model is right behind it, reaching the number 6 position on the same leaderboard. To put those rankings in context, Gemma 4 is outcompeting proprietary models that carry 20 times its parameter count. These metrics validate Gemma 4's utility for highly rigorous tasks, from processing strict JSON outputs to generating offline code. The empirical data proves developers no longer need to compromise on logical capabilities to maintain their data privacy. Below the workstation class, Gemma 4 includes the Effective 2B and Effective 4B models, engineered specifically for mobile and IoT devices. This diagram illustrates the legacy pipeline for on-device speech. An audio waveform passes into a transcription model, outputs a text string, and feeds into a large language model. That pipeline introduces severe friction, compounding latency at every handoff and taxing host memory. Gemma 4 bypasses this friction using a unique native multimodal architecture. A 40 millisecond frame duration audio encoder allows the model to ingest spoken language directly into the transformer block, collapsing the fragmented pipeline into a single inference call. The immediate hardware benefits are near-zero latency processing and the preservation of battery life on edge devices like Android phones. These edge models also process variable resolution images and video, enabling offline optical character recognition and chart understanding directly on the hardware. Eliminating intermediary transcription models is the key to making real-time AI responsive on mobile hardware, where every millisecond of latency and megabyte of RAM impacts the user experience. Previous generations of Gemma were governed by source-available terms that restricted certain deployments. Gemma 4 shifts to an Apache 2.0 license. This legal framework is the critical mechanism unblocking commercial enterprise adoption. Apache 2.0 grants developers unrestricted commercial use, full fine-tuning rights, and removes all share-alike requirements for derivative works. This legal shift grants developers digital sovereignty over their data and their local infrastructure. Revisiting the hallucination incident involving Senator Blackburn through this legal lens reveals why the event is so significant. Because the Apache 2.0 weights were permanently and legally distributed to the public, Google's only available recourse to the political pressure was to shut down their own hosted user interface. These models, executing entirely locally on consumer machines, operate without the safety filters mandated by centralized cloud providers. A highly permissive open-source license physically breaks the traditional kill-switch model of AI safety enforcement. The combination of MOE inference efficiency, native audio encoders, and Apache 2.0 licensing creates a new deployment reality. Frontier-level reasoning and complex data processing are permanently decoupled from massive centralized data centers. Local hardware cleanly bypasses centralized control structures. Offline instances running on tools like Ollama remain completely immune to external moderation or retroactive safety patches. With context windows extending up to 250,000 tokens, these local models can process massive, highly sensitive internal documents in environments with zero internet connectivity. The design of Gemma 4, prioritizing small, fast, and open models, demonstrates that centralized, cloud-style containment is no longer the only viable path for frontier AI. This architectural diagram defines the modern AI deployment stack in 3 distinct tiers: the base model, the application logic, and the user interface. The base model is now just a raw, unpolished utility. It is no longer the central locus of safety or alignment. Mitigating hallucinations, filtering outputs, and ensuring systemic safety rests entirely in the application logic layer. Application engineers must architect their own strict UI guardrails and API moats around these open weights. Deploying a raw, unmoated open model to consumers risks recreating the exact failure Google experienced during the initial launch. In the Apache 2.0 era, the power of frontier AI belongs to the developer, and so does the resulting liability.